Hello everyone. Today we are going to discuss about colloidal state. First of all, I would like to ask you something. Is there any difference between the states of water and milk? In the case of water, it is in liquid state. What about milk? Is it also in liquid state? In order to get a clear answer, we can examine the constituents of milk. Milk contains 87.2% water and 12.8% of other materials like fat, carbohydrates, minerals, proteins and other minor constituents. So, milk is a dispersion of the aforementioned materials in water, and the state of milk is actually a colloidal state. So, what is actually a colloidal state mean? A colloidal solution is a heterogeneous system consisting of two phases. First phase is the dispersed phase, which consists of colloidal particles having diameter roughly in the range 1 to 1000 nanometer. Second phase is the dispersion medium, which consists of the solvent or the medium in which the colloidal particles are dispersed. There are lots of other colloids that we come across in our daily life like foam, smoke, detergents, gels, blood, paint, cosmetics, etc. Now, here we can see a beautiful scenery here, isn't it? Actually, it is a colloid and its optical property are responsible for the beauty of this picture. Yes, mist is a colloid present here, and when sunlight passes through mist, it scatters the light, and thus we could see the path of light as rays in this picture. This ability of colloids to scatter the beam of light is known as Tyndall effect, named after the scientist John Tyndall who discovered the effect. Do you know what is a solution? A solution means a solute dissolved or dispersed in a solvent, and three different types of solutions are true solution, colloidal solution and suspension. Now, what do you mean by true solution? A true solution is a homogeneous mixture of solute and solvent. Example, salt solution, sugar solution, etc. In a true solution, the solute particles cannot be seen even with a powerful microscope. The entire solution passes through the filter paper. The solute particles do not show any Tyndall effect. The particles do not settle due to gravity, so stable in nature. Now, what is a colloidal solution? A colloid appears to be homogeneous, but actually it is a heterogeneous mixture of solute and solvent. Example, starch in water, milk, etc. In a colloid, the size of particles is in between 1 to 1000 nanometer, and the dispersed particles can be seen with a powerful microscope. The particle can pass through ordinary filter paper. The particles show Tyndall effect, and they do not settle due to gravity and hence stable in nature. Now, what about suspension? A suspension is a heterogeneous mixture of a solid dispersed in a liquid or gas. Example, chalk powder in water, soil in water, etc. In a suspension, the size of particles is greater than 1000 nanometer. In a suspension, the dispersed particles can be seen with naked eyes. The particles cannot pass through filter paper. They may or may not show Tyndall effect. The particles may settle due to gravity, thus unstable in nature. Thus, the main difference between true solution, colloidal solution and suspension is the difference in the size of the particles. In true solution, the particles are having size less than 10 raised to minus 7 centimeter. In colloidal solution, the particles are having size in between 10 raised to minus 7 to 10 raised to minus 5 centimeter. And in suspension, the particles are having size greater than 10 raised to minus 5 centimeter. A true solution cannot show any Tyndall effect, while the colloidal solution can show Tyndall effect, and in the case of suspension, it can show Tyndall effect only until the particle settles down due to gravity. We can go to the classification of colloidal system. Both milk and gel are colloids, but are they of same type? No. So, there are different types of colloids, and we can classify these colloids mainly on three bases. First one is on the basis of states of aggregation of the two phases. Second classification is based on interaction between dispersed phase and dispersion medium. And third classification is based on the particles of the dispersed phase. First classification based on states of dispersed phase and dispersion medium. There are 8 colloidal systems present on this basis. When the dispersed phase is a gas and the dispersion medium is a liquid, then the colloidal system is known as foam or froth. Examples are soap, foam, whipped cream, etc. And if the dispersed phase is gas and dispersion medium is solid, then the colloidal system is known as solid foam. Examples includes rubber, styrene foam, cake, bread, etc. As we mentioned earlier, mist, fog and cloud are colloids, and here the dispersed phase is liquid and dispersion medium is gas. Thus the system is known as liquid aerosol. In the case of milk, cod liver oil, cream, etc., the dispersed phase and dispersion medium are liquids, and they belongs to the category known as emulsion. Gel is another colloidal system where the dispersed phase is liquid and dispersion medium is solid. Examples are cheese, boot polish and jellies. If dispersed phase is a solid and dispersion medium is a gas, then the colloidal system is known as a solid aerosol. And examples includes smoke and dust storm. When the dispersed phase is solid and dispersion medium is liquid, it belongs to the colloidal system sol. Examples are paint, starch dispersed in water, etc. Can you believe that colored glass and gems are also colloids, and here both the dispersed phase and dispersion medium are solids, and the system is known as solid sol. Now, we can discuss about the classification based on interaction between dispersed phase and dispersion medium. On the basis of the interaction between dispersed phase and dispersion medium, colloids are classified into two: lyophilic colloids and lyophobic colloids. In lyophilic colloidal system, as the name indicates, the dispersed phase has high affinity for the dispersion medium. They are also known as reversible salts due to their ability to reconstitute on adding dispersion medium after separation. They are quite stable and do not coagulate easily. Lyophilic salts are highly solvated, and the particles of the dispersed phase are covered by a layer of the dispersion medium. Lyophilic colloids can be synthesized easily by simply shaking or warming the substance to be dispersed with the medium. Examples of lyophilic colloids are gelatin, gum, starch, protein, rubber, etc. Now, what about lyophobic colloids? In this type of colloidal system, the dispersed phase does not have an affinity for the dispersion medium, so the colloid is not readily formed. They are also known as irreversible salts, and they cannot be reconstituted by simply adding the dispersion medium after precipitation. They are unstable and coagulate easily on adding electrolyte, shaking or heating. Lyophobic colloids can be prepared by special methods and requires a stabilizing agent. Lyophilic colloids can protect lyophobic colloids from electrolyte. They form a protective layer around lyophobic particles, as we could see in the image here. Examples of lyophobic colloids are salts of metals like gold, silver, etc. and metal sulfides. Next is the classification based on the particles of the dispersed phase. On this basis, colloids can be classified into macromolecular colloids, multimolecular colloids and associated colloids. What are macromolecular colloids? The molecules of natural and synthetic polymeric substances possess very high molar masses which may range from thousands to millions. These are called macromolecules, and these individual molecules themselves size in the colloidal range. Colloidal dispersion of macromolecular substances are called macromolecular colloids. Examples: salts of starch, gelatin, protein, rubber, etc. In the case of multimolecular colloids, individual particles of the dispersed phase consist of aggregates of atoms or small molecules having diameter less than 1 nanometer. Here, the particles are held by weak van der Waals forces. Example: aqueous gold sol, aqueous sulfur sol, etc. Now, what are associated colloids? Certain substances which behave as normal electrolyte in dilute solution show colloidal properties at higher concentration due to the formation of aggregated particles of colloidal size known as micelles. Such colloidal systems are known as associated colloids. Now, we can take a look into the micelles and critical micellar concentration. Surfactant ions or molecules can collect together to form clusters of colloidal dimensions known as micelles, as we mentioned. Micellar formation occurs only above a certain minimum concentration of the surfactant. This is called critical micellar concentration. Above critical micellar concentration, the interfacial surfactant monolayer is not able to accommodate any more surfactant ions or molecules, and they coagulate to form micelles. The structure of micelles in aqueous medium is approximately spherical. The non-polar hydrophobic tails are directed towards the center, while the polar hydrophilic head points towards the periphery. In the structure of a soap micelles in aqueous solution, the hydrocarbon tail of each monomer anion is directed towards the center, while the polar COO- group is on the outside. Many COO- groups of the micelle have solvated Na+ ions bound to them. Non-ionic surfactant micelles may contain 1000 or more monomer units per micelle, but ionic surfactant micelle generally contains only 20 to 100 units on account of electrostatic repulsion between their head groups. Next, the preparation methods of colloidal solution. Lyophilic colloids can be prepared by just heating the solid with the liquid dispersion medium, whereas lyophobic colloids cannot be prepared just by heating. They need to be prepared by some special methods. The two methods by which the lyophobic colloids can be prepared are as follows: dispersion method and aggregation method or condensation method. Dispersion method. In this type of preparation method, the larger particles are broken down into particles of the range of colloidal particle size. Some dispersion methods are mechanical dispersion, electrodispersion and peptidization. Mechanical dispersion. In this method, solid and the liquid dispersion medium are poured into a colloidal mill to form a colloidal sol. Next is Bredick's arc method, that is electrodispersion method. This method involves the electric disintegration of the coarse material. Hydrosols of metals, example platinum, silver, gold, are prepared by this method. The metal electrodes are kept at the two sides of the arc, which is enclosed by deionized water. The excessive heat provided by the spark vaporizes some traces of the metal and water gets condensed by the vapor. Some amount of KOH is added to water as a stabilizing agent. Next method is peptidization. The process of bringing a freshly precipitated substance into a colloidal state is called peptidization. and this is usually done by adding a small quantity of peptizing agent. Very often the peptizing agent is an electrolyte. Example, ferric chloride is added to a freshly prepared precipitate of ferric hydroxide, which converts it into a colloidal salt of reddish brown. Next is the aggregation methods. In this method, small particles are aggregated to form colloidal size particles. First one is double decomposition. Double decomposition is an example for aggregation method. Example is arsenious oxide is mixed with hydrogen sulfide to form arsenic sulfide salt. The excess amount of hydrogen sulfide is removed by passing stream of hydrogen. Next is a reduction. Example is a violet aqueous salt of gold can be prepared by the reduction of auric chloride with stannous chloride in very dilute aqueous solution. Next, oxidation. When hydrogen sulfide is passed through a solution of sulfur dioxide, it forms sulfur salt. The freshly prepared lyophobic colloidal solutions generally contain considerable quantity of electrolytes or some other soluble impurities. The presence of small excess of electrolyte will destabilize the salt. It is therefore necessary to reduce the concentration of these impurities to an optimum minimum. Three different methods are generally adopted for the purification are ultrafiltration, dialysis and electrodialysis. Ultrafiltration. In this method, the colloidal particles are separated from the salt through filtration. The colloidal salt is passed through an ultrafilter paper that filters only the dispersed phase, that is the colloidal particles. The dispersion medium along with impurities passes through the filter paper. A fresh dispersion medium is added to the separated or filtered colloidal particle to make a pure colloid. A normal filter paper cannot be used for this method and its pores are large that cannot filter the colloidal particle. The salt along with all of its components will pass through it. Due to this reason, an ultrafilter paper is used, which is prepared by soaking the filter paper in a colloidal solution. This solution is a 4% solution of nitrocellulose in a mixture of alcohol and ether and is hardened by formaldehyde. The pore size of an ordinary filter paper is 0.7 to 25 micrometers, whereas the pore size of an ultrafilter paper is 0.0015 micrometers. Besides this, ultrafiltration is a slow process, so its speed is increased by applying pressure or suction. Next method is dialysis. Dialysis is the process of removing soluble impurities from colloidal system by allowing them to diffuse through a porous membrane such as parchment membrane or cellophane membrane, which is permeable to solvent molecule as well as to impurity ions and molecules but not to colloidal particles. Here, the impurity molecules or ions diffuse smoothly through the membrane by virtue of their small size and fast rates of diffusion. The colloidal particles, on the other hand, are mostly kept back on account of their larger size and small rate of diffusion. Third method is electrodialysis. This method is also based on dialysis. It uses the same apparatus and salt in the bag that were used in the dialysis. The only difference is that it makes use of electricity. The bag filled with impure salt is suspended in the water. Electrodes are present in the container that produce an electric field across the bag. Electrodialysis is used for the salts that contain only one type of electrolyte as an impurity. One electrode is positively charged and another is negatively charged. The negative ions present in the colloid contained in the bag will come out by passing through the membrane and move to the positively charged electrode. Similarly, the positive ions from the bag moves towards a negatively charged electrode. Electrodialysis is widely used in blood purification as it is a fast process. The impure blood is passed to artificial kidney apparatus. The impurities from the blood diffuse out through the dialysis membrane, whereas the colloidal particles of blood remain in the blood. The purified blood is obtained and is passed back into the body of the patient. With this, I am concluding this session. In the next session, we shall discuss about the properties of colloids. Thank you.